Hi viewers, this is Sri Ramulu. So today's topic is important, most important, that is a transverse wave equation. Okay, so already we have derived a longitudinal wave equation in a bar. Now transverse wave equation. See transfer wave. Transfer wave equation in a bar. The transverse waves in bar propagates with different velocities. This is known as dispersion. So already we know how the when the if it is a prism, and if light goes through the prism, then it is divided into seven different colors. Then it is called dispersion, and their velocities are also different. So like this here also, in the bar, the waves transfer waves travels in different direction with different velocities. That is why it is called dispersion. The material of the bar behaves like a dispersive medium. Yes. Let us consider dispersive medium means which can disperse the transfer wave, that is called dispersive medium. Let us consider a bar of length L having uniform cross section area cross section alpha as shown in figure. It is this one. The position coordinates is taken along bar and transverse displacement as y. So transverse displacement upside. By bending the bar, lower part is compressed and upper part is elongated. So for example, if it is a bar, if you bend this and this side and this side, then what happens? It becomes like this, isn't it? See, so this lower part is compressed, means its size is decreased, but upper part is elongated, means its length is increased. Here length is decreased, upper part length is increased. Okay, by bending. Elongation means extended. At the middle part of the segment, there is no change in length. Okay, so in the middle part means here. Generally, more bending occur at the end only. So while we are going in this direction, bending gradually decreases. So at the middle, no bending will occur. Here more bending, here no bending. Okay. The axis passing through this segment of the bar is called as neutral axis. If any line passes or axis passes through this point, that is called neutral axis. The forces acting on upper and lower parts of the neutral axis are equal and opposite, and hence cancelled. Yes. So at this part down here, down forces, and the same thing up the upside only. Okay. So here also upside force act and downside force act. Then only these two ends bends. Therefore, the total longitudinal force is zero. However, bending moment will act on the bar. So forces are zero, but bending moment is never zero. It is bending in both sides. So something is also acting. Bending here nothing but work only, isn't it? Bending is nothing but work. Why? Work is equals to force into displacement. Same formula we use here. Okay. So here bending moment is denoted by m is equals to distance into force, or force into distance. So it is a total distance is integrated. Here see, so this is a bar, it is a bar, small bar, and this bar forces are applied, small forces are applied. Then this part may end downside. So then change in length is r, and here to here always the distance is same, that is a capital R. So that is just like a radius of curvature. Why? Because when you bend like this, then it can form a small circular radius, or it is form a sphere. Then this distance is what? It is a capital R, no change. But actually it is here, when it bends like this, then change in its length is denoted by R, change in length. So total change in length is integrable. So here actually dm is equals to r into df we have to write. So bring d this side or integrate on both side. Here integration differentiation cancel, here integration comes. So this is the equation 1, right, where r is change in length. Okay. From Young's modulus. So what is Young's modulus? Y is equals to longitudinal stress by longitudinal strain. So stress formula force by area by change in length by original length. It is a formula for this one. It is a formula for this one. Here force is df, small force we apply df by area in small force in small area d alpha by what, change in length is small r, original length is capital R, so small r by caps R. Now so right, it is in the multiplication from capital R by small r we get. Okay, from this df is equals to, from this df is equals to what, so if this factor bring this side, then ry d alpha by r. Substituting df value in the equation 1. Equation 1 is this one, so here we have to substitute. Yes, substituted, then r into r square we get, and the remaining are constant. Keep a d alpha this side only. So if in k, so actually if a k is the radius of gyration, then what happens, k square is equals to integration r square d alpha by alpha. Okay, so actually k square is what, r square d alpha, it is r1 square plus r2 square d alpha by whole alpha square we get. So like this, alpha only by alpha we get. So from this, so we can write this generalized formula as integration r square d alpha only. So integration r square d alpha by alpha. From this bring alpha this side, k square alpha integration r square d alpha. So in the place of this we can write k square alpha. Yes, k square alpha. Let it is equation 3. Next, radius of curvature r is given by, r formula is what, so it is actually separate formula. It is in bending moment only occur. R is equals to what, 1 plus dou y by dou x whole square whole power 2 whole square not whole square, 3 by 2 whole power 2 by dou square y by dou x square. But here bending moment is less. Bending moment less means dou y by dou x slope is, when it is not bending, generally bar cannot bend more, they bend less, so that is why it's a slope value is 0. So that means this factor is 0. Then what happens, simply 1 by this factor will remains. Is it? That is the reason why it is 0. Generally bar the bends, but less, very less bending will occur. Now substitute r value where, here. Okay, substituted here, and we can write like this. Already it is by, again by r can be written as upside, right? Okay, now let it is equation 4. When the bar is bent as shown in figure, bending moments and shearing forces will act on it as shown in figure. Shearing, bending moments means like this bending. Shearing force means a force which can change the shape of a substance. So its shape is changed. Original shape is like this. Now it is bent like this. So that is why its shape has changed. Okay. Now bending moment acting on the left side of the segment. See here, bending moment acting on the left side of the segment, act in anti-clockwise direction, left side. So when we apply the force like this and like this, so it is anti-clockwise and it is clockwise. Left side anti-clockwise, right side is clockwise, and hence treated as positive. Okay, anti-clockwise, here we have to take positive, while bending moment acting on the right side of the segment is in clockwise direction, treated as negative. Okay, so that is why here all are positive and this side are negatives. Similarly, shearing force acting in upward direction is taken as positive. Shearing force. So here shearing force is this one. Only left side is taken. In equilibrium means at equilibrium position. The turning moment arises due to the bending moment, and shearing forces on the segment will be zero. Okay, so bending moment at this position. So here from here to distance is actually dx. So that is why then here x, then it is x plus dx this side. Okay. So here x plus dx. At x, mx and fx force, and at dx plus dx only this force has taken. Okay, no need to take this one, no need to consider. So it is take this one and sorry, this and this force is taken. Bending moment, this bending moment left side and right side bending moment and left side force. Okay, mx left side, it is right side, it is right side. Okay, but it is also bending moment. Why? Force into distance, it is also bending moment. Here dx is small. Then applying the Taylor series, what for this one? Mx plus dou mx by dou x into dx. When you have like this, according to Taylor series, we have to expand like this. This is also can be expanded. Fy at x plus dou fy at x by dou x into dx. Here see, mx and fy is also separated. Here y, and substitute these two things, right? Substitute this is and this is here and here. Here into dx is there, don't forget for fx. So mx as it is, in the place of mx plus dx is this one. In the place of, so mx as it is, in this place this is substituted here, and only in the place this one. So see, into dx is there. Now open the bracket by multiplying minus. Here also open the bracket by multiplying minus and dx. Here it is minus minus, all are minus. Dx here, dx into dx, here dx into dx, here also dx. But here dx into dx square, we know that is as, and these are the same thing. These two gets cancelled actually. Okay, these two gets cancelled. So remaining factors are 1 2 3 factors present. Among them, last term can be neglected. Why? Because dx is small, its square what happens again very small. So that is why this factor is completely neglected. Now what are these two factors? Okay, so bring this is this side. Now it is minus, it this side plus, but here we have the minus. This minus is multiplied here. Now m value. So already from equation 4 is given here. See, so in the equation 4 we have derived there. What is that? See, once again let me go back. Equation 4. What is equation 4? Y k square alpha dou square y by dou x square. Okay, y k square alpha dou square y by dou x square, that is substituted here. Okay, and now by arranging writing like this, already square is there for differentiation, and like one more differentiation will get, so it becomes cube. So remaining all are constant taken outside. Here minus, don't forget. Now under bending condition, now applying forces under bending conditions, dfi change in, so left side force and right side force. So changes is this one. Okay, so according to Taylor series we can write like this, we know already. So just now we have separated according to Taylor series. And now f, this 2f gets cancelled. Right, sorry, this 2f gets cancelled. Here it is minus into this one, and now we get minus. So it is a dfy. Already fy formula we know. What is that Fy formula? Just now see Fy formula, this one. Substitute that Fy formula here. Okay, so when we substitute here in the place of Fy, minus y k square alpha dou cube y by dou x cube. So these are the constant factor taken outside. So already cube is there. Again if you differentiate, it becomes 4. Minus minus plus here. Right? So this is from Newton's second law of motion. So force is equals to mass into acceleration. Dou square y by dou t square is acceleration. And we know the mass can be written as rho alpha dx. Why? Rho is equals to mass by volume. Rho is equals to mass by volume can be written as area into length. And bring these two things this side, then m is equals to rho alpha dx. Now comparing 7 and 8th equation, Fy dfy both side. So this two side also equal. Here alpha dx gets cancelled and remaining same only. Okay, yk square rho. So rho bring this side. Then what happens? Y by rho k square. So we know y by rho can be written as c square, or c is equals to under root y by rho. So then it is c square is equals to just y by rho only. So that is why in this place c square is written. So this is a wave equation in transverse wave in a bar. So in transverse waves for bar, this is the equation, and its general solution is C. Actually, general wave equation, we know we cannot compare these two things, isn't it? Why? It is a fourth power is there, right? So left side are same, but right side fourth power is there. We cannot compare them. So leave it like this only. And general solution for transfer waves. So general solution for transfer wave, it is a lengthier here. Hyperbolic functions are there and a normal functions also there. Y is equals to cos omega t plus theta, big bracket, a cos h omega by vx plus b sin h omega by vx plus c cos omega by vx plus d sin omega by vx. These two are hyperbolic functions and these two are normal functions. 4 points, 4 different things are there. So that is a 4 constants will get. Boundary conditions, it is important. Everywhere boundary conditions are most important. At fixed point, at the fixed end or can be written as clamped, there will be no displacement and a slope at that point is 0 at all instant of time, means at any time. Its displacement is 0 and slope is 0. Okay, so displacement 0, slope is 0 at x equals 0. Again displacement 0, its slope is 0 at x equals to L. So there in the previous question, y is equals 0 means at x equals 0 only we have written. But at x equals 0, here two conditions are coming. Right? Two conditions. At x equals 0, two conditions. At x equals 0, two conditions. 4 conditions we get. Why? Because 4 constants are there in the equation. A, B, C, D. If you have to get 4 constants, then 4 conditions we must apply at both ends. At first end 2 conditions, at second end 2 conditions. For fixed one only. For free one what? At the free end, bending moments and shearing forces are 0. So bending moment is dou square y by dou x square is equals to 0. Shearing forces dou cube by dou x cube is 0. So here at x is equals to 2 conditions. At x equals to L, 2 conditions. Okay, here don't forget dou square, dou cube square, cube square, cube square, cube. And if you compare here simple logic, y0 no differentiation, first differentiation, second differentiation, third differentiation, right? Y0 first no differentiation, first differentiation, second differentiation, third differentiation at L. This is a simple logic you must keep in mind. Okay, so at x equals 0, at x equals 0, no differentiation, it's a differentiation one time, second time, third time. At x equals to L, no differentiation, first time, second time, do it twice, thrice differentiation. Okay, so that is logic. Okay friends, don't forget, it is very important for the exam point of view. Okay, thank you.